Now let's look at how to build a convolutional neural network. This slide shows a figure of a simple convolutional neural network that can be used to classify objects in an image. It starts with a convolutional layer. This convolutional layer will identify low-level features in the input image. Examples of such features are lines or colors or other low-level objects. The second convolutional layer will identify high-level features. In this case, if you want to identify different types of animals, it will look for features like tail, ear, nose, or an eye. Then we end with a fully connected layer with a softmax output. This will summarize all the features of an object and classify it into a specific object, such as a dog or peacock. Note that there is no specific relationship between the number of channels in the layers. For example, in this figure, we start with 3-channel image, 1, 2, 3. Then we go to an 8-channel first layer, and then a second convolutional layer of 4 channels. The number of channels are simply chosen independently. It is common that the width and height shrink as you move deeper into the network. However, this is not necessary. It depends on the stride. If you use a stride of 1, the resolution will not shrink. If you have a greater stride, you will see smaller and smaller layer, as you can see here in this figure. Also note that although this is a convolutional neural network, we still have a fully connected layer. That is, it's the presence of the convolutional layer that makes it a CNN. But a CNN does not only consist of convolutional layers. In that case of classification, it's very common to have fully connected layers at the end of the convolutional neural network. Now let's revisit the softmax operation that was used at the end of the neural network in previous videos. We use softmax for multi-class classification. Softmax consists of n outputs, one for each class that we want to classify. We will normalize values of these outputs. Summing them together will result in 1.0. The chart shows how the weighted sums as the blue bars. These are the weighted sums of the neurons. After we apply the softmax, they will have been reduced to the red bars, as you can see here. And the sum of these red bars will be 1.0. And when we use the softmax layer, we want to use the cross entropy loss function. This is the formula of it. Let's discuss now why we use fully connected layer at the top of the network. It's used to summarize the features in the entire image. The top convolutional layer here will consist of high-level features at specific location in the image. However, each neuron is in the fully connected layer will be detected a specific object. In this example, a specific animal, let's look at an image of peacock. Add the neuron indicating if there is a peacock in the picture or not. Now let's discuss why we are using a fully connected layer at the top of the network. Well, it's used to summarize the features in the entire image. The top convolutional layer will consist of high-level features at specific locations in the image. However, each neuron in the fully connected layer will be detecting a specific object. In this example, a specific animal. Let's take a look at the neuron indicating if there is a peacock in the picture or not. The neuron will look for if there is a lot of eyes in the picture. So it will have high values of weights that connect to the feature map that is detecting eyes. Because if there are a lot of eyes in the picture, there is a high probability of that picture actually being a peacock. Note that there are many complex dependencies when trying to classify images, so it's often beneficial to have multiple fully connected layers on the top. Now, to gain some more insights into the properties of the convolutional layer, let's now compare the number of weights in a convolutional layer with the number of weights in a fully connected layer. For a fully connected layer, the number of weights will equal the number of the layer of neurons in the layer times the number of neurons in the previous layer. For the convolutional layer, it will depend on the number of the channel in the layer times the kernel size times the channel in the previous layer. This results in fewer number of unique weights in a convolutional layer than in a comparable fully connected layer. And this is because convolutional layer applies weight sharing and it is sparsely connected. Let's now also look at the comparison between the number of computations needed for a convolutional layer versus a fully connected layer. This will be determined both by the number of neurons in a layer and the number of weights per neuron. For a fully connected layer, the number of weights per neuron will be the number of neurons in the previous layer, so the number of computations will be the number of the neurons times the number of neurons in the previous layer. For the convolutional layer, the number of weights per neuron is the number of channels in the previous layer times the kernel size. The number of the computations will now be the number of neuron in the layer times the kernel size times the channels in the previous layer. So n minus 1 refers to the layer in the previous layer. The convolutional layer typically have fewer calculations than the fully connected layer, and this is due to the sparse connections in the convolutional layer. Let's now talk about max pooling. Max pooling operation can reduce the resolution of a layer that is reduce the width and the height, but without using any weights. We simply take a group of pixels or group of neurons, for example, 2 by 2, and then output a single value. We will output the maximum value among the group of neuron outputs. The idea is that if you have found a feature somewhere in the image, it's sufficient to know approximately where this image was, and you don't need to know exactly where it is. A convolutional operation is applied across all channels. So although we apply the convolution on 3 channels, we still just end up with a single value. The max pooling operation is applied separately per channel. So max pooling operation will result is the same number of output channels as there are input channels to the operation. Let's break it down. So convolution operates across all channels. When you apply a convolution filter to an image or a feature map that has multiple channels, for example, an RGB image with 3 channels, each filter actually spans all those channels simultaneously. For example, suppose the input image has a shape height times width times channels, 32 by 32 by 3. We apply one convolutional filter kernel of size 3 by 3 by 3 that this 3 covers all channels. This gives one scalar output for that position, combining the information from all input channels. Even though the filter reads from 3 channels, it produces one output feature map, so one channel. If you have 64 filters, you will get 64 output channels. But in terms of max pooling that operates per channel independently, pooling, for example, max pooling or average pooling, does not mix information across channels. For each channel separately, it slides a small window, for example, 2 by 2, and picks the maximum value in that window. It reduces the spatial size, the width and the height, but keeps the number of channels the same. If your input has shape height times weight times the channels, and you apply 2 by 2 max pooling with stride 2, the output will be the height divided by 2 times the width divided by 2 times the channels. Let's take an analogy. Think of convolution like a chef testing a dish, combining all ingredients, which is the channels in this case, to form one flavor, one output. Think of pooling like sampling each ingredient separately to find the strongest flavor in its own group per channel. Now let's talking about the padding, which is a technique to handle the edges of the image. This figure shows pixels in green at the bottom here in the image, followed by 2 layers of neurons, where A and B are neurons in the top layer. Note that I eliminated the 2-dimensional image here to simplify the figure. Let's consider the neuron in the first layer. It has a kernel size of 3 because it's connected to 3 of the input pixels. Now let's consider the neuron that is at the edge of the figure. At the very left, we see that one of the pixels that is input to that neuron is missing. That is why we introduce padding. So we simply create a pixel that has a value 0, so we can give some kind of input to the neuron. If we would not apply padding, the resolution of the layer would be reduced compared to the input image, even if we used a stride of 1. We often use something known as same padding. That means that the resolution of the convolutional layer will have the same resolution as the input image, assuming a stride of 1. The number of padding values depends on the kernel size. If we have a large kernel size, we will need to add more pixels as padding. Finally, we have mentioned how a neuron has a receptive field equal to the kernel size. But we can also talk about the receptive field with respect to the original image. For example, in this example, we can see that the neuron A has a receptive field of 4 pixels in the original image, even though its kernel size is just 2. So this is a combination of the kernel size for neuron A as well as the kernel size of the neuron that is feeding neuron A.